now it should be. Let me see.
Testing? Yep. Great.
So we resume with Tracy's lectures on your lecture 2, right?
Yep, great. All right, welcome back everyone after the break. So when we left off, we were talking about the estimate for thermal freeze-out and the cross-section that you needed to get the right amount of dark matter through that mechanism. I'll say that if you look at my slides on Indico, you will see that there are a few extra slides, which are the bonus calculation for that. I'm not going to go through that in detail, but the key things you would learn from those slides. One is that the estimate that we just did works provided that you actually need to deplete the dark matter density in the early universe. As I said before, if your dark matter mass is at the EV scale, you could get the right dark matter abundance just by freezing out while still relativistic. Now, that corresponds to the hot dark matter regime. So as we said, that probably can't be 100% of the dark matter. We can set an upper limit on the amount of hot dark matter that is at the level of 1% of the dark matter. My slides have a reference for that number. But the calculation that we just went through is the cold dark matter regime. If the dark matter is at the EV scale, you could also get the right abundance without it. The other thing, the bonus calculation in those slides is what happens if instead of 2 dark matter particles in the initial state, you have 3 dark matter particles in the initial state, or 4 dark matter particles in the initial state. You can redo the same estimate that we just did in that case, and what you find is it goes through more or less the same way, but the sort of characteristic mass scale, we argued in thermal freeze-out, it's, the cross-section is like an order 10 number divided by 100 TeV squared. So if you say the characteristic mass scale for the two-body case is 100 TeV, which we'll come back to later in this lecture, then if you have 3 or 4 body annihilation, the characteristic mass scale just goes down. So that's a fun exercise to work through yourself with or without the help of the slides if you're interested. All right. So what I want to do in this lecture is, we've talked about one way to get the dark matter abundance through thermal freeze-out. Because these thermal freeze-out scenarios are an important benchmark for a lot of experimental searches, I want to spend a little bit of time talking about, if you did have this kind of abundance mechanism, what would the history of thermal relic dark matter be post-freeze-out? What kind of constraints can we put on the mass and interactions of thermal dark matter from cosmology? And then, having sort of set those cosmological boundary conditions, I want to outline some widely used benchmark models, both for heavy weakly interacting massive particles and for light sub-GeV particle dark matter that gets its abundance through thermal freeze-out. And if time permits at the end, I'll then talk through a number of ways that these scenarios can be modified. Axions will be tomorrow, and the direct and accelerator searches for these will also be tomorrow. So this will mostly be about the model space. Okay, so let's just think a bit about what happens to thermal relic dark matter after freeze-out. So we have gone through this. So, we had the plot on the previous slides. The dark matter abundance has dropped exponentially. It's frozen out. It's reached this plateau. Now we're going forward into the subsequent universe. The number density of dark matter is really boring. At this point, it's just diluting with the expansion of the universe. But this annihilation process that we talked about previously is still happening. It's just happening at a rate which doesn't deplete the dark matter density by very much after freeze-out. So let's just look at the consequences of that annihilation. So during radiation domination and after freeze-out, we can ask about the fraction of dark matter that annihilates per Hubble time. So the rate of dark matter annihilation per unit dark matter particle goes like n times sigma v. So the overall annihilation rate per volume is n squared sigma v if we divide out by the number density of dark matter. N sigma v gives us the annihilation rate per dark matter particle. Multiply, and then we want to multiply by a, so if we want the annihilation rate per Hubble time, we want to divide by a Hubble time, which is equivalent to multiplying by h. So this gives us this dimensionless number. So recall at freeze-out, this fraction was order 1. That corresponds to an order 1 fraction of dark matter annihilating per Hubble time. Post-freeze-out, this fraction is always going to be less than 1. So how does it scale? Well, in the radiation-dominated epoch, the Hubble parameter scales like t squared, and n sigma v, if sigma v is constant and doesn't change with respect to redshift, then this is just going to go like the number density of the dark matter, which is redshifting roughly like temperature cubed, since temperature goes roughly like 1 over a. So we see that this rate is going to drop off just as like 1 power of the temperature. Now at freeze-out, this ratio was roughly 1. It's proportional to the temperature of the universe. So at late times, the fraction of dark matter that annihilates in a Hubble time is going to be roughly the temperature of the thermal bath divided by the temperature at freeze-out. So if the universe is expanded by a factor of 10 since freeze-out, temperature has dropped by a factor of 10. Now, order 10% of the dark matter is annihilating away in a Hubble time. So that means that we know how much energy is being injected by these processes per baryon over a Hubble time. It's roughly 5 GeV times this fraction, because there's 5 GeV of dark matter for every baryon in the universe. So what that means is that the amount of power that we're injecting into the universe is enough to, if this was the only thing it was doing, it would be enough to change the kinetic energy of every baryon in the universe by an order 1 factor if the freeze-out temperature was about 5 GeV, which corresponds to a mass of about 100 GeV. So if you've got 100 GeV annihilating thermorelic dark matter, then the subsequent annihilations will always be sort of at the level of the kinetic energy of the baryons per baryon. So that's throughout radiation domination. We had a radiation domination assumption in here. And yeah, the other thing is that the way that this scales, if you go to lighter dark matter so that freeze-out was later, that means TF is smaller, this ratio is increased. So what we see here is like the residual annihilations of thermorelic dark matter can potentially be significant. That's a signature that we'll look for, and they'll be larger for lighter dark matter particles. So that's through radiation domination. Once we hit matter and dark energy domination, the energy injection falls off more rapidly at low temperatures. But once we get into matter and dark energy domination, we also start to not just rely on the cosmological average density of dark matter. We have galaxies and galaxy clusters, which can have much higher dark matter density than the cosmological average. There, these residual annihilation signals can give rise to potentially large indirect detection signals, and Professor Calore's lectures are going to focus on that. So indirect detection is really cool, and I spent a lot of my time thinking about it, but I'm going to leave that to Francesca later in the week. But let me just talk very briefly about one example of the consequences of this kind of energy injection. So let's talk about the CMB epoch, for example. The temperature of the universe at recombination is about 0.2 eV, as we've heard, and the CMB is emitted not that long after matter radiation equality. So I'm going to take the crude estimate of assuming that the universe is radiation dominated from freeze-out all the way down to the CMB epoch. This isn't exactly right, but the factor that you miss by doing this wrong is an order 1 factor. So that means that if I had a thermorelic dark matter that was annihilating away that had a freeze-out temperature of TF, then the amount of power injected per baryon over a Hubble time at recombination from the residual annihilations of this dark matter particle is going to be like 1 eV times 1 GeV divided by T freeze-out. And we know that you need about 10 eV, 13.6 eV of energy to ionize 1 hydrogen atom. So that means that if we had a freeze-out temperature of say like 0.1 GeV, then so with a mass scale of around 2 GeV, that would provide enough power at recombination to ionize. Yeah, I'll try. To ionize all the hydrogen. Okay, we'll try it, yeah. To ionize all the hydrogen in the universe over a Hubble time. Now that's if all the power goes into ionization, which won't be exactly true. But when you do this calculation in detail, you find that actually an order 1 fraction of the power does end up going into ionization. So this would be a huge effect, right? I mean, we know that the CMB was emitted. If the universe stayed fully ionized at the CMB epoch instead, that would be very startling. Like we would not observe the cosmic microwave, the photons would not free stream. We would not observe the cosmic microwave background radiation that we see today. So these residual annihilations can potentially have a big effect just because there's a lot of energy stored in dark matter compared to the amount of energy that you need for things like ionizing hydrogen. So actually, we can do a lot better than just saying, well, you can't ionize all the hydrogen in the universe at the CMB epoch. The CMB constrains changes to the ionization level post-recombination at the level of 10 to the minus 3. So, if when the universe was 1 million years old, 1 in 1,000 hydrogen atoms got ionized, we would actually know about it. So that tells us that, maybe we could constrain injections that are like 10 to the minus 3 times 13.6 eV per baryon, which corresponds to a freeze-out temperature up to the TeV scale. So a consequence of these, this is basically just a plug for indirect detection, a consequence of these thermal relic scenarios, if the annihilation continues after freeze out, is that you can potentially have pretty substantial changes to the ionization and thermal history of the universe at late times. Now, when you do the calculation in detail, not all the power goes into ionization. For most standard model final states, some of the power goes into neutrinos that escapes. Even the stuff that goes into photons and electrons, some of it heats up the gas rather than ionizing it. Some of it goes into distortions of the CMB. But a detailed calculation does find that you can exclude dark matter annihilating to anything in the standard model except neutrinos with a thermal relic cross-section after the emission of the CMB for masses below about 10 GeV. So this is the result of that calculation. So everything above these colored lines is ruled out by not messing up the CMB. And again, the mechanism for messing up the CMB here is that you ionize more hydrogen and the free electrons scatter the CMB. Everything above the colored lines is ruled out by these constraints. Different colored lines correspond to different standard model final states. Red and pink lines are annihilation straight to electrons or photons. All the other colored lines are everything else in the standard model except neutrinos. And this black dashed line is this thermal cross-section that we talked about. So that's a pretty powerful bound. What it means, the major loophole, so does this mean that you can't have thermal relic dark matter below 10 GeV? Well, not quite. It means that you can't have thermal relic dark matter that annihilates to non-neutrino standard model states with the thermal relic annihilation cross-section in the CMB epoch. So the loophole is you find a way to turn off the annihilation at late times. This can be done in multiple ways. If you have both dark matter and anti-dark matter, for example, and the anti-dark matter all annihilates away in the early universe, you will suppress the CMB signal by a lot. If the annihilation requires some other partner particle that goes away in the early universe, again, you'll suppress the signal by a lot. If the annihilation is suppressed at low velocities, which can happen naturally in models where what's usually the leading order term, the velocity-independent annihilation, just goes to 0 through selection rules, then if the annihilation is suppressed with the v² factor, that can also kill the CMB constraint. But this is why when we talk about accelerator and direct detection searches for dark matter below about the 10 GeV scale, these constraints will limit what kinds of classes of models you can have. You basically have to ensure that you don't annihilate at the full thermal relic rate after the CMB epoch. So that is my taster for indirect detection. And I'll also say that there are scenarios where the annihilation is actually enhanced above its early universe value at late times. These are even more constrained by these CMB bounds. So that is my taster of how tiny fractions of the dark matter annihilating in the late universe can potentially have large observational effects. And I'll leave the rest of that to Francesca Colore and ask you just to remember that below 10 GeV, we have these bounds which force us to look at models where the annihilation at late times is suppressed. What about the other probe that Valerie told us this morning? What about our Big Bang nucleosynthesis? So BBN occurs around temperatures of 0.1 to 1 MeV. It's constrained by observations of the light element abundances. So the presence of thermal relic dark matter can affect this in multiple ways. The first is similar to the CMB. Just as at the CMB epoch, dark matter annihilation could produce particles that ionize the hydrogen, annihilation in the BBN epoch can produce energetic particles that can catalyze or inhibit the reaction network that produces nuclei. Again, if you had a freeze-out temperature of 5 GeV, the amount of energy that you're injecting is comparable to the kinetic energy of individual particles, the temperature of the thermal bath. We know by construction that's comparable to the mass splitting between the proton and the neutron. It's comparable to the relevant mass splitting for deuterium. So you can set non-trivial constraints on dark matter annihilation from BBN, although usually the limits from either the CMB or from indirect detection are stronger in that regard. However, there's also a very general constraint from Big Bang nucleosynthesis on dark matter models, especially thermal dark matter models, that basically just comes from measuring the expansion timescale at that epoch. So the measurement of helium in particular gives us a clock for the cosmic expansion because, as you heard in Valerie's talk, the amount of the helium yield is largely determined by the amount of neutrons that are still around in the universe at the time at the time of nucleosynthesis, which is determined once the temperature drops below the neutron-proton mass difference. The abundance of neutrons is determined by the rate of the decays and scatterings that convert them into protons. Has to bind into helium to be stable. That means that the final amount of helium you get is pretty sensitive to the relative timescale for, on one hand, turning neutrons into protons through the decays or through weak interactions, and on the other hand, the cosmic expansion timescale. So the helium abundance basically allows us to do a sensitive measurement of H. And since BBN occurs during radiation domination, H is sensitive to the number and temperature of relativistic species making up the radiation bath. And those relativistic species can include the dark matter. So the contribution of relativistic species to the... So there is a BBN constraint like just directly on annihilation, which can apply to 100 GeV or 1000 GeV dark matter if it has a large enough annihilation rate. But what this clock is sensitive to is the presence of dark matter particles that have mass scales around the MeV. Okay, so they're freezing out around the time of BBN. So another way to say this is that BBN allows you to do a measurement of N effective, the number of effective relativistic species in the bath. We usually express this in terms of the number of effective neutrino species through this formula. If the energy density of the extra species, I is rho I here, the ratio of that energy density to the energy density in photons can be written in this parameterization. So in the standard model, we expect N effective to be about 3, just a little over 3. The correction away from 3 here is just that this number assumes a simplified treatment of the temperature of the neutrinos, and really that treatment has some small corrections, which get you 3.044 instead of 3. So again, our measurement of N effective is essentially just a measurement of the clock during BBN, which mostly comes from helium. This plot here is showing a constraint on extra degrees of freedom around the BBN epoch, and you know how well you would do at constraining these extra degrees of freedom as a function of your precision on the helium measurement, which is the x-axis, and your precision on the deuterium measurement, which is the y-axis. So as long as your deuterium measurement is pretty good, mostly what affects your result is how well you can measure the helium. So the other thing to keep in mind, so how might you change this N effective parameter? Well, the simplest way to change it is just by having extra relativistic degrees of freedom in the bath associated with the dark matter or with particles that couple to the dark matter. So this is what happens if dark matter is still relativistic at the start of Big Bang nucleosynthesis. So this is relevance for sort of MEV scale dark matter candidates. It could itself contribute to N effective. That's where this part of the freeze-out curve starts already when BBN is occurring. But what if you say, all right, but what about if BBN is down here or down here? Okay, so by this time the dark matter abundance itself has dropped exponentially. It's probably not contributing very much to N effective. So then the question becomes, okay, but what is the dark matter annihilating to? If the dark matter annihilates to some invisible dark radiation, so as the dark matter goes down, the dark radiation goes up, then that dark radiation will itself contribute to N effective. So you can't hide the dark matter signal that way. If instead the dark matter annihilates to neutrinos or other standard model particles, then the question becomes, well, okay, what is it annihilating to? Because the energy density in relativistic species is strongly sensitive to their temperature. If the dark matter annihilates mostly to photons and electrons and very little to neutrinos, it will heat the photons and electrons relative to the neutrinos. That will change the relative temperature of the photon and neutrino baths, which changes the standard model contribution to N effective. And it can go in either direction. If the photons get hotter relative to the neutrinos, it decreases N effective. If the neutrinos get hotter relative to the photons, it increases N effective. So unless you have a fine-tuning such that the branching ratios to neutrinos and to other standard model stuff are finely tuned so that you increase the temperatures of the two baths by exactly the same amount, annihilation to any standard model states will generically modify N effective, just due to changing this temperature ratio. So all of these effects taken together really sort of corner thermorelic dark matter that becomes non-relativistic and freezes out around this BBN epoch. Unless you have this fine-tuning, it doesn't really have a lot of places to hide. So there are lower limits on the dark matter mass that vary depending on what the spin of the dark matter is, like whether it's a fermion or scalar, and exactly what it annihilates to. But here are some recent papers which looked at these carefully, but these mostly allow you to exclude thermorelic dark matter with a mass lower than about 4 to 14 MeV. And, you know, with our sort of like factor of 20 estimate, you can see that this corresponds to freeze out occurring during BBN. There are ways to get around this, but mostly the way that they get around it is by having a situation where the dark matter doesn't actually get produced until after BBN in the first place, so they require some theoretical tweaking. So this is the important constraint that mostly sets the lower bound of the valid thermorelic window to about the 10 MeV scale. Now, there's another, okay, so that's constraints on the parameter space. Now, when we think about so we've talked about the thermal history of thermorelic dark matter after freeze-out. We've talked about its potential effects on the CMB. We've talked about its potential effects on BBN. Now, there is another potentially important event in the life of thermorelic dark matter, which can leave observational consequences, which is when it kinetically decouples from the standard model. So this freeze-out epoch corresponds to the dark matter no longer being in full thermal equilibrium with the standard model. But even after that happens, it's possible for there to be interactions between the dark matter and the standard model to keep the dark matter at the same temperature as the standard model. An analogy for this is even after the electrons decouple from the photons at the CMB epoch, the electrons and photons actually stay at about the same temperature, down to about redshift 150 to 200, just because elastic electron-photon scatterings are enough to keep them hot. So that kinetic equilibrium between the dark matter and the visible matter can be maintained by elastic scattering of dark matter off the relativistic standard model particles. The generic picture is that usually the kinetic equilibrium is maintained for longer than the chemical equilibrium, because for kinetic equilibrium you can scatter off the standard model radiation, which is very abundant. Whereas for the freeze out, you have to scatter off other dark matter particles whose density is getting exponentially depressed. If we have a tight coupling between the dark matter and photon baryon fluids, then that damps the dark matter density fluctuations, just as we talked about last time in terms of if there was a drag force between dark matter and baryonic matter at the CMB. They can only damp fluctuations that have already entered the horizon, but basically all the fluctuations that have entered the horizon at the time of kinetic decoupling will be suppressed. And there's an old but good review on this by Torsten Bringmann from 2009. So the effect of maintaining a coupling between the dark matter and baryons for a long time is to suppress power on small scales, and you can work out roughly what the scale of acoustic oscillations is, and you get a number that looks like this. So as you can see from that, so TKD here is the temperature of kinetic decoupling. The number that's been substituted in here is a 50 MeV decoupling. You can see that this is the mass scale associated with those modes in the present day. This mass scale is about 3 × 10⁻⁶ solar masses. So kinetic decoupling puts in a cutoff in the matter power spectrum. You expect it to be there. If the decoupling temperature is at tens of MeV or higher, that cutoff scale is really, really tiny. So this is a potentially observable signal, but practically not very observable signal. In cases where the dark matter is heavier than sort of the MeV scale, as in this, so it doesn't run into these BBN bounds that we just talked about, typically what it's scattering off in the standard model bath is electrons. Dark matter doesn't like to scatter off photons very much because it's dark. So a very common scenario in this case is that the dark matter, if it stays decoupled down to the electrons become non-relativistic, then once the electron number density drops rapidly at that transition, the dark matter also decouples. So it's actually somewhat difficult, unless there's a big coupling to neutrinos, for the dark matter to stay kinetically coupled to the standard model much below about the 100 keV scale. And so the typical scale associated with this kind of process is the typical mass scale associated with this kind of process is rather large. And I think there's an exercise for you to do that works this out in more depth. But if the dark matter is lighter than lighter than MeV scale, if it obeys one of those loopholes that allow us to evade the BBN bounds, or if it's not a thermal relic at all, then you potentially can have significant changes to the matter power spectrum. Again, I know that you talked about this last week, so I'm just going to mention this briefly as a constraint. So we have observational probes of the matter power spectrum from large-scale structure and also from galaxy observations. The large-scale structure bounds are shown on this plot. So this goes down to about 10 to the 11 to 10 to the 12 solar masses. And recent studies of small subhalos in galaxies get us down to about the 10 to the 7 to 10 to the 8 solar mass scale. But so these bounds here correspond, these halo masses of 10 to 11 to 10 to the 12 solar masses correspond to modes that enter the horizon around the KeV mass scale. So this is sort of the simple reason why we can constrain KeV scale dark matter with bounds on the matter power spectrum. It's that if you're looking at dark matter much heavier than that, you're talking about modes that entered the horizon much early on and correspond to scales that we're just not very good at probing yet. So this is my summary of the warm dark matter bounds that I know Kafir talked about last week. We can study the properties of smaller dark matter halos down to the scale of 10 to the 7 to 8 solar masses. This buys us about an order of magnitude. This allows us to probe roughly 10 keV dark matter particles that have decoupled from the standard model around the 10 keV scale. These probes include the Lyman alpha forest, fluctuations in the density of cell streams, the strong gravitational lensing of quasars, and observations of faint Milky Way satellite galaxies. So these constrain thermal dark matter below the roughly 10 keV scale. They also constrain other scenarios such as ultralight dark matter, self-interacting dark matter, and scattering between dark matter and baryons. And there is this nice review by Bechtel et al. In the context of the snow mass process that talks about constraints on dark matter properties from halos. It's worth mentioning that while I'm focusing here on what kinds of limits there are on thermal relic dark matter, these limits will also apply to dark matter that has a high temperature and a large free streaming length for reasons unrelated to its coupling to the standard model. For example, dark matter that has been heated up by interactions within a dark sector or that just had a large temperature in the early universe. I also just want to note the little caveat here that I've been talking about this mostly in terms of temperature, but for dark matter that's not in thermal equilibrium, temperature isn't usually the full story. You have to track the full phase space distribution, and you can see these papers for some examples of how to do that calculation. This figure is just showing explicitly how as you change the dark matter mass, you induce a cutoff in the matter power spectrum. This x-axis here is showing the halo mass in solar masses. This is the sort of 10 to the 7 to 10 to the 8 solar mass scale. This is a paper by Bannock et al. From 2021 looking at stellar streams. This is their estimate of how much substructure there is in the Milky Way from stellar streams, and these different lines are showing the kinds of cutoffs that you would get with 10 keV mass dark matter. But if you're talking about 100 GeV or TeV mass dark matter, then you're more in this regime that I mentioned over here. The kinetic decoupling is typically at the MeV scale or higher, and you end up with cutoffs at mass scales down around between 10 to the minus 6 solar masses on 1 solar mass. Okay, so putting this all together, what can we say about the thermal window for dark matter? Well, at the light end, warm dark matter and BBN limits constrain thermal relic dark matter lighter than the roughly 10 keV and 10 MeV mass scales respectively. You should probably put just a little 10 in front of each of these. So in general, we say that the thermal relic window starts at about 10 MeV and goes up. There are some theoretical tricks that you can play to try to open the space from 10 keV to 10 MeV. It's really hard to simultaneously evade the BBN bounds and the warm dark matter bounds. So that's one end of the window. What about the other end of the mass range? What's the maximum mass for which this thermal relic scenario can work? So there, the standard limit comes from saying, well, if the dark matter is too heavy, it's really hard to get it to annihilate fast enough to get the appropriate abundance today. So there is a bound just from unitarity, which is another word for probability conservation in quantum mechanics, that sets a strict upper limit on the total cross-section for dark matter to annihilate into anything as a function of the angular momentum of the colliding particles. So J here is the total angular momentum quantum number of the system. This sigma VRL total is bounded above in each partial wave by this contribution. So you might say, okay, that's fine. Like we'll make J very large. I'll say a little bit more about that in a moment. But generically, we find that it's usually only the lowest partial waves that contribute significantly to annihilation in the early universe. In higher partial waves, the cross section is typically scales with more powers of the velocity at late times. But if we know a set of partial waves that contribute significantly to the depletion, we know what VREL is roughly at freeze out, and we know what the dark matter mass is, then we can compute this upper bound and see how that compares to the annihilation cross-section that we need, our 20 over 100 TeV squared number, to get the right abundance. Alternatively, if we say, all right, let's just set that as, say that we want those two things to be equal, we want this bound to be equal to the thermal relic cross-section that you need, then this relation allows us to solve for MDM and find a maximum value for MDM in that scenario. And if M is larger than that value, then this cross-section, this upper bound will always be below the cross-section that we need. So let's just throw in some numbers, consider saturating the bound with just the lowest partial wave. then what we'll have is that the cross-section, this was the estimate that we got before for the thermal relic cross-section, which if you put in the numbers for it, comes out to be just about 2 × 10⁻26 centimeters cubed per second. Like we said before, we'll equate that with 4 pi over m squared VRL, where m here's the dark matter mass. You put in the numbers, and that's going to give you a dark matter mass around 300 TeV. Now, a more careful calculation finds an upper mass bound that's often quoted as around 100 to 200 TeV, which is valid when only a few partial waves contribute. I will say that it's actually quite hard to saturate this bound. If you want to fully saturate this bound, you often need long-range interactions and/or strong couplings. Some of the earlier studies say for composite dark matter there's no upper bound because you can have lots of partial waves contributing. You know, high partial wave collisions correspond to things colliding with a big impact parameter. If the object's very extended, then maybe that's okay. But there's an argument in Smirnov and Beacom from a few years ago that in fact that if you've got sort of shallowly bound states of dark matter, then they'll get disrupted by plasma effects before they can annihilate. And so for composite dark matter, the real upper mass limit is about 1 PeV, which is about 1,000 TeV. So this upper limit is a little bit fuzzy, but somewhere in the roughly 100 TeV to 1,000 TeV range, it just becomes very difficult for very generic reasons to get an annihilation cross-section that you need to get the right amount of dark matter today. Now, the limit can be evaded in a couple of different ways. Easiest way is just to say, all right, maybe the dark matter doesn't get its abundance through freeze out after all. There are various non-thermal production mechanisms that are possible. You can make some heavier state and have it decay out of equilibrium in the early universe. During inflation, you have gravitational particle production that can produce heavy particles. There are some ideas where if you produce primordial black holes in the early universe, when they evaporate through Hawking radiation, they can evaporate to anything in the spectrum, including dark matter. So yeah, that's another form of like quasi-gravitational particle production. And there's this nice Snowmass review on early universe model building that has descriptions for a number of ways to make ultra-heavy dark matter. It's also possible to get ultra-heavy dark matter just in the thermal relic scenario, but you need to modify the cosmological history. One way to do this is if there's a large injection of entropy into the standard model bath, so for example, some other currently unknown particles that annihilated away in the early universe and heated up the photons, that has the effect of diluting the dark matter relative to the photon bath. So that can allow you to open up the window for heavy dark matter because you make more of it early on, it gets diluted by this process. You get to the right relic density in the end. I worked with Poya Asadi and other collaborators on showing that if you have a first order phase transition in the dark sector, because that phase transition is very inhomogeneous, it can lead to enhanced annihilation in the early universe. For these very heavy dark matter particles, the problem is that they don't annihilate well enough through freeze out. So if you have ways to dial up the annihilation rate, i.e. by increasing the effective density, then that can help. It's also possible that the dark matter is lighter at the time of freeze out, but after freeze out, it forms into large many particle bound states. So that can be a situation where the particle dark matter that you see today is actually very heavy, but it's made up of lighter constituents that were produced by thermal freeze out. So so now we've talked about the thermal window, we've talked about the upper and lower bounds, we've talked a little bit about what's out beyond the top of the thermal window, and tomorrow we'll talk about what's on the other side of the thermal window. But to summarize, here's what we've got for thermal relic dark matter. For thermal relic dark matter below about 5 to 10 MeV, BBN can often be used to set stringent constraints. Where loopholes exist, thermal relic dark matter below about 10 keV is independently constrained by warm dark matter bounds, and for dark matter heavier than about 100 TeV, it's challenging to get a sufficiently large cross-section. Okay, so now let's focus on what happens within this window. I told you before that the GeV to TeV window is often called the classic WIMP region. So this was on one of my bonus slides, but if we look at this number for the cross-section, if we say this is 20 over 100 TeV squared, and we say that let's assume that this is a weakly coupled theory, then that annihilates through the tree level, then we might parametrically expect this cross-section to be some coupling squared divided by some mass scale squared, if there's no hierarchy of masses in the theory. So if that's the case, we can set this to our estimate from before. We can solve for m as a result of this, and we can see that, it's parametrically going to be like alpha times 100 TeV divided by square root 20 in this case. So now if we say, okay, let's suppose that we had alpha that was comparable to the weak interactions, so that's alpha around 10 to the minus 2, then this would give us 1 TeV divided by square root 20, which is about 250 GeV. So this is what's sometimes called the WIMP miracle, the statement that we get the right cross-section naturally if you get weak interactions and a few hundred GeV mass scale. So that has motivated a lot of focus on dark matter candidates that are associated with the weak scale. But as we've discussed, that's not the full thermorelic range. This mechanism works fine up to 100 TeV and down to the 10 MeV scale. Okay, so what I want to do in the remainder of my time, though, is talk a bit about benchmark models, both for this classic WIMP regime and for the lower mass stuff. And then tomorrow we'll talk about how to test them. Okay, so that's sort of like the cosmological bounds on what we can do. Now we're going to talk about some candidates. Okay, so the most famous dark matter candidate is the lightest supersymmetric particle in theories of supersymmetry. This is less true than it was 10 years ago, but I think it's still true that supersymmetric candidates are probably on aggregate the most studied possible dark matter candidates. So in supersymmetric, this is my few slide introduction to SUSY. In supersymmetric theories, every particle has a superpartner. Fermions have boson superpartners and vice versa. And supersymmetry has a number of nice features. It's a new symmetry of the standard model. The additional particles cancel what would be large predicted contributions to the Higgs mass. So that's an independent motivation from dark matter. This can help with the hierarchy problem. They also help with gauge coupling unification. And there's a nice review article from a few years ago if you want to learn more about SUSY. So in unbroken symmetry, the particles and their superpartners would have the same mass and closely related interactions, but we'd better break that supersymmetry because we haven't found any of the superpartners yet. So if they exist at all, they had better not have mass equal to their known counterparts. But there are ways to break supersymmetry such that separate the mass of the particles, but the interactions still remain fixed by the supersymmetric structure. So in this case, these SUSY theories inherit a huge structure of interactions from the standard model. If you know the interactions of the standard model particles, you also know the interactions of their superpartners. So many quantities in SUSY can be calculated just from knowing the masses of the superpartners. These are just some examples. So this is the photon-electron interaction in the standard model. This tells you about interactions between the superpartner of the photon, the superpartner of the electron, and in their several variations. Now, the presence of these SUSY interactions would naively imply some peculiar behavior. For example, they open up new channels for rapid decay of the proton. Now, this is pretty experimentally excluded. The experimental limit on proton decay corresponds to lifetimes of over 10 to the 33 years at the moment. So if we want SUSY to exist in the universe, we'd better do something to stop this. So the usual approach is to impose an additional symmetry called R-parity so that the superpartners can only couple in pairs to the ordinary particles. So we say superpartners have R-parity -1, ordinary particles have R-parity +1, and the product of R-parities before and after an interaction must be conserved. So if we have no superpartners in the final state, we'd better have an even number of superpartners in the initial state. But that also means that the lightest superpartner can't decay. Okay? We can't have a situation where we've got one superpartner in the initial state, 0 superpartners in the final state. If it doesn't have other superpartners to decay to, it can't decay at all. So then this looks like a nice dark matter candidate. That if we want to have supersymmetry and we don't want to have proton decay, we're given some kind of stable particle in the spectrum almost inevitably. Furthermore, if we made any of the R-parity odd superpartners in the early universe, we would eventually produce this particle by decays. And because its interactions are inherited from the standard model, the generic behavior here is to have a weakly interacting stable particle. So in much of the SUSY parameter space, the relevant dark matter candidates are called neutralinos, and so these are a very long-standing benchmark for possible dark matter searches. So the neutralinos are neutral fermions, which are superpartners of the neutral standard model bosons. There are also charginos. We don't want them to be the dark matter. We'd like the dark matter to be neutral. So the Higgsino is the superpartner of the Higgs boson. The Wino corresponds to the SU2 gauge bosons. The Bino corresponds to the gauge boson of the electroweak U1 gauge group. Now, in general, the physical states of definite mass are not going to line up exactly with these gauge eigenstates. They're going to be admixtures of the various neutral components. If the lightest supersymmetric particle is the lowest mass of these neutralinos, then it can be a good dark matter candidate. Now, I should say, like, even when we talk about the minimal supersymmetric standard model, the MSSM, it has a really large number of parameters. So often for these benchmarking purposes, people will look at more restricted subsets of the SUSY parameter space, like the constrained MSSM or the phenomenological MSSM. It's also true that, like, not every point in parameter space in SUSY gives us a good dark matter candidate. Much of the naive parameter space has already been excluded due to null searches, and there's much more that doesn't give you a good candidate that has the right relic abundance. This is an example from a paper by Bramante et al. So this is fixing a bunch of parameters in the MSSM, but varying some mass parameters associated with the Higgsino, Wino, and Bino. And this sort of curved colored region is the surface in that parameter space upon which, and the surface on this restricted 3D parameter space on which you get the right relic density. So there's space where you get the right relic density, but it's not a guarantee. And the right panel of this is just showing, as I said, that LSP is an admixture. It's just showing how much of the LSP is in this Wino state. Okay, so I'll show you some examples later about sort of how much of this SUSY parameter space we can currently constrain, but this is like a long-standing classic benchmark. The other long-standing classic benchmark for WIMP dark matter is that some of the SUSY scenarios that are least constrained experimentally are those where the neutralino is an almost pure Higgsino or gaugino. But if that's what we want, we don't actually need supersymmetry to have that kind of behavior. We can just ask, sort of the stupidest thing that you might do once you've learned about the standard model is say, what if we just added more particles that were in multiplets of the standard model SU2 gauge group? The interactions here are, again, like supersymmetry. They're fully determined by the gauge structure. In this case, we don't have all the additional structure of lots of superpartners. We're just adding one multiplet. And the mass of that new multiplet can be determined if we require it to explain the full relic density. This plot is showing the mass scales that you get for adding different additional SU2 multiplets to the standard model. This is the 3-plet, the 5-plet, the 7-plet, the 9-plet, the 11-plet, and the 13-plet. The red and blue points correspond to, it can be either a scalar or fermion. In SUSY, the Higgsino and Wino are fermions. But if we're just saying, okay, let's just add some extra SU2 multiplets, they don't have to be fermionic. So that yields a discrete set of relatively heavy benchmark WIMP models. What about at the low mass end of the spectrum? So, that's the argument that there are some examples of ways that you can generate heavy thermal dark matter. Well, there's a long-standing argument due to Lee and Weinberg that you may have seen, which says you can't have dark matter below the 2 GeV mass scale. Now, I mean, this, of course, would be a great surprise to many people. So where does this argument come from? So the Lee-Weinberg bound assumes that the dark matter interacts with the standard model through the Z boson and that it got its abundance through thermal freeze-out. So, when I wrote down this estimate before, alpha squared over m squared, that assumes that there was no hierarchy in the problem, that the mediator that couples the dark matter to the standard model has roughly the same mass as the dark matter itself. But if the dark matter was 2 GeV and was annihilating the standard model particles through the Z boson, so through some kind of diagram like dm goes through a Z boson. This pen is not very good. Goes through a Z boson into standard model stuff. Then this propagator has a 1 over mz squared in it. So if the momentum transfer is small, if the momentum transfer is associated with the dark matter mass, the propagator is going to have a 1 over mz squared in it. When we square that, that's going to give us a 1 over mz to the 4 in the cross-section. Dimensional analysis then tells us that we might expect a cross-section that looks like this times some coupling. Now, there could be a lot of channels for this annihilation. We'd again get sort of a similar argument to our unitarity bound, so maybe we shouldn't keep the alpha squared in there. Maybe we should just look at sort of the geometric coupling from m squared and mz. Now, if you put those numbers in and you plug them into our calculation here, we want to get this annihilation cross-section with an upper bound that scales like this result, then you would find that the m has to be greater than about the GeV scale. If it's much smaller than this, the mass hierarchy between the dark matter mass and the mz is too large and the annihilation cross-section will be too small. So now looking at this with the eyes of, okay, maybe dark matter is not a WIMP, we'd say dark matter below this mass scale is actually fine, but if it's a thermal relic, we'd better not annihilate through the Z. To get the right annihilation cross-section, we need some kind of new mediator to the standard model. And the Higgs won't work and the W won't work because the same argument applies there. They're about the same mass as the Z. So if we want dark matter that is a thermal relic that is below the GeV scale, we need to think about new mediators to the standard model. So the field's approach to this has mostly been a very bottom-up approach where you just say, all right, what kinds of interactions can we write down between the dark matter and the standard model that are consistent with Lorentz invariance, with the symmetries of the standard model, and that are not expected to be suppressed by a large mass scale. So these are the two most commonly used benchmarks. These are terms that you can add to the Lagrangian that correspond, these are often called the scalar and vector portals, and they basically correspond to adding a new scalar mediator or a new vector mediator. The scalar mediator can mix with the Higgs boson of the standard model through an operator that looks like this. Here phi is the new scalar, h is the standard model Higgs, and or you can add a new vector, a new just U1 vector boson, and that vector can mix with the standard model through the through their field strength terms. So this is sometimes called the kinetic mixing portal, or the dark photon portal, or the vector portal. So these operators are special because they're dimension 4 operators in the standard model Lagrangian, so they're not suppressed by any heavy mass scale, and we might naively expect them to be there with a modestly large cross-section. And these are the only two options that satisfy the mediator being a standard model neutral boson, so it's not charged under any of the standard model symmetries. It has a renormalizable interaction with the standard model, and the interaction respects all standard model symmetries. If you're not wedded to it being a bosonic mediator, you can add a new fermion, which carries fermion number, same as the standard model fermion number, and then you can build a Lorentz invariant operator that looks like this, where we couple the new fermion to standard model neutrinos and the Higgs. What this leads to, this is sometimes called the neutrino portal. It leads to the new fermion mixing with the standard model neutrinos once you break the electroweak symmetry. And of course, if you don't care about dimension 4 operators, and you don't care about things being neutral under the standard model symmetries, you can go much further than this. You can allow for higher dimension interaction structures. We'll hit one of those when we talk about the QCD axion. You can have mediators that carry standard model quantum numbers that couple to, say, baryon number or lepton number as well. But this is, in the bottom-up approach, these are the two scenarios that are most commonly considered. Okay, so let's just go back to our freeze-out calculation and ask how much would things change if you had this kind of situation. So we've now introduced two new particles, the dark matter and the mediator. So there are two general scenarios here. Either the dark matter can annihilate through the off-shell mediator into the standard model particles, so just like this diagram, but instead of the Z, we now have a mediator, a new light mediator. So that's one possibility, and that's the generic behavior when the mediator is heavier than the dark matter. The other possibility is that the dark matter just annihilates straight into the mediators. So and then subsequently the on-shell mediator decays into standard model particles. And that's the generic behavior when the mediator is lighter than the dark matter. In the first case, the calculation is basically exactly the same as before. The annihilation cross-section is controlled by the coupling of the dark matter to the mediator to the standard model, and the mass of the mediator. If the mediator is heavy enough and we can integrate it out, that basically just acts as an effective coupling between the dark matter and the standard model. We can constrain that by requiring that we get the right freeze-out cross-section, and then we can look for that target coupling in direct experiments and in accelerator experiments. In the second case, the freeze-out calculation is really similar, provided that the mediators stay in equilibrium with the standard model throughout. If they don't, it's more complicated. You can see this paper for all the weird things that can happen in that case. But if the mediators do remain in equilibrium, then the only thing that's different is that now the freeze-out cross-section really only depends on this coupling. So it depends on how the dark matter talks to the mediator, but not on how the mediator talks to the standard model. So this scenario often leads to cases where the scenario is relatively easy to probe through indirect detection, which probes the same physics, the same annihilation physics as the freeze-out, but it's much harder to get at in terrestrial experiments. Okay, so last slide, and then I'll wrap up. So Okay, so this is the basic picture of a freeze-out. These are the basic benchmark models for thermal freeze-out that people think about. And then there are lots of variations. So there could be more than 2 particles in the initial state. These are my bonus slides at the end of lecture 1. So a classic example of this is the strongly interacting massive particles studied by Unit Hochberg and colleagues in 2014. So what happens here, and this is as discussed in lecture 1, as discussed in the bonus slides for lecture 1, what happens there is that instead of the maximum mass scale being about order 100 TeV, it becomes the geometric mean of the Planck mass times more powers of the temperature at matter radiation equality, which is about 1 eV. So basically, as you increase the number of particles n in the initial state, your characteristic mass scale goes down. For 3-body annihilation, it becomes about 1 GeV. So the strongly interacting massive particle scenarios consider pretty strongly interacting dark matter in the MeV to GeV range, which can get you the right relic density with 3-body interactions. As we talked about earlier, the annihilation could be either suppressed or enhanced at late times and low velocities relative to what was happening during freeze-out. And if you're below 10 GeV, you almost have to be in one of these scenarios, where the annihilation is suppressed at late times and low velocities to evade CMB constraints. You could also have annihilation enhanced at late times and low velocities. And in fact, those minimal dark matter models that I told you about, which couple to the W and Z bosons, generically have strongly enhanced annihilations at low times because this behavior is generic when there are mediators much lighter than the dark matter around. And then we can have larger variations. We can have fully or partially secluded dark sectors. Some behaviors that can happen there, the dark matter can convert some of its mass density into kinetic energy, so the number density falls, but the dark sector heats up, and that's called cannibalism. I was talking before about scenarios where kinetic decoupling happens well after freeze-out, but that doesn't necessarily have to be true. If decoupling happens during freeze-out, the transition from exponential depletion is actually triggered by the kinetic decoupling, and then the abundance is controlled by the scattering cross-section rather than the annihilation cross-section, so that's called an Elder scenario. There's one other really important benchmark, which is freeze-in dark matter, which I will talk about at the start of tomorrow, and then we'll go into how you test all these things. So we'll stop there for today. Thanks very much. There's my key, yes.
Any questions? Okay.
Hi, thank you for the lectures. So regarding the portal models,
Yeah.
since the vector or the scalar are massive, could it be that they are the dark matter itself? Like,
Yeah.
would that work?
Yeah, so that's right. So that's I'll talk. I think I'll talk a little bit more about this next time. Yeah, so you can say maybe the dark matter just couples directly to the standard model. Maybe it doesn't need to go through this portal. So the thing is that if you have that kind of portal interaction, the particle is unstable generically, right? So like here, so for example, a kinetically mixed dark photon couples to the charged standard model particles, so it can couple to a loop of fermions and then like decay into photons or neutrinos, or directly into electrons if the mass is high enough. So, and similarly for the scalar, like this kind of portal opens up channels. So like that phi h dagger h, that opens up channels for it to decay through the mixing with the Higgs boson. So that doesn't mean it can't be dark matter, but it means that you need to make sure the lifetime is long. The easiest way to do that typically is to make the mass scale very tiny. So dark photon dark matter is a viable scenario. It's mostly a viable scenario for ultralight dark matter. So I'll say a little bit more about ultralight scalar and vector dark matter when we talk about axions tomorrow. But yeah, so it absolutely is, but not usually coincident with this thermal relic scenario.
Thank you.
Here?
Thanks for the talk. In the case of dark matter that works as bound states of maybe other dark matter candidates,
Yeah.
do we have only the bound state after
Good.
freeze out, or do we have both?
You could have both. So you could have, just like in the standard model, you have both like hydrogen atoms and an ionized component. You could potentially have both. So it's a model dependent question, how much of the dark matter ends up in the bound states and how much would still be in the unbound component. So there are atomic dark matter models, which are really similar to the standard model. So you have a residual ionization fraction, just like you have a residual ionization fraction in the CMB after recombination. There are also scenarios where there's kind of a runaway instability process and almost all the dark matter gets bound into big clumps. So it's a model-dependent statement, but you're right. In principle, both components can be there.
Okay. Do you know the constraints on maybe cosmological constraints on bound states?
So they're good. It's pretty model-dependent. So there are some cases where the presence of bound states in a spectrum allows you to do like an S-wave annihilation through an effective S-wave annihilation through S-wave formation of a bound state that subsequently decays. If your main annihilation is P-wave, that can actually be the dominant annihilation signal in something like the CMB. But in general, if all that's going on is like your dark matter is clumping into bigger bound states of dark matter, there's usually not much in the way of cosmological constraints unless either your bound states get so extreme that they collapse into black holes, and then you're in that primordial black hole limits regime that I talked about in the first lecture. Or, yeah, I mean, I think that's mostly, I mean, I guess if you can have a situation where the dark matter, so if the thing that's making the bound states is that the dark matter has a really strong self-interaction, then if you have a significant amount of the dark matter that's not stuck in bound states, then you can potentially get constraints on that self-interaction from looking at the distribution looking at the distribution of dark matter in halos. But if the dark matter basically all ends up in like tightly bound states that then interact very little with each other, the limits on that are pretty weak. You can try to do things with like halometry and weak gravitational lensing studies that are like the equivalent of those primordial black hole searches, but look for things that are not collapsed to the degree that a black hole is, so more extended objects. But the constraints get weaker pretty rapidly as you start saying, okay, it's not a point particle anymore. It has some extended size. There are some constraints from sufficiently strongly interacting heavy bound states running into direct detection experiments could lead these to like these distinctive multi-scatter tracks, but you need the interaction with the standard model to be pretty substantial for that to happen. So yeah, I don't know of a lot of really generic constraints on big dark matter bound states. There's some work, if you look up like dark matter nuggets by people like Catherine Zurek and Moira Gresham, then there's been some work on like big multi-particle bound states in that context.
Okay, thanks.
Any more questions, comments?
Oh, I did want to say one thing. I looked up that constraint on primordial black holes that goes very deep. That's actually the CMB accretion constraint. So PA stood for Planck. Somehow, I don't know why they picked PA to be the abbreviation for Planck. Yeah, I guess it's Planck accretion. So yeah, the mechanism there is if you've got these black holes around the CMB epoch, the plasma can accrete onto the black holes that can produce that can produce additional radiation as the plasma gets accelerated in the accretion process. And that can set a pretty strong limit for black holes in a specific mass range. But if they're too light, they don't accrete efficiently. Yeah, so it's a good question.
I have more. I'm here. Okay.
Yeah, great.
I have more clarification.
Sure.
You said that for very heavy dark matter particles, it's difficult to achieve the right abundance.
Yeah.
Can you explain me again why this is the case?
Yeah, so it's difficult to achieve the right abundance through the thermorelic mechanisms, so through this freeze-out mechanism that we talked about. And that's just because, so it's because to get the right abundance, you need to have a particular annihilation cross-section, right? So this roughly 20 over 100 TeV squared or 2 × 10⁻26 centimeters cubed per second. Those are the same number if you just put it in. So the issue is that there is a general argument based on, so if you've done quantum mechanics scattering problems, when you do quantum mechanics scattering problems, you'll find that the cross-section goes like some scattering amplitude squared divided by k squared, okay, where k is the momentum in the problem. This is basically a geometric cross-section bound. It's saying that, you know, the momentum sets a length scale for the problem, the momentum squared sets an inverse length scale, the momentum squared sets like an inverse area for the object. You can't scatter more often than 100% of the things that scatter that area scatter with the particle. Okay, so that's sort of what I mean by probability conservation says you can't scatter with a probability of more than 1. So your cross-section is sort of just limited by your geometric de Broglie cross-section. That geometric cross-section just corresponds exactly to this. We can take the VRL from this side, put it on this side, and you would see that this is just 4 pi over k squared times this factor for the partial waves. Okay, so the unitarity bound comes into play when this upper limit on the cross-section becomes smaller than this cross-section that you need to get the right relic abundance. Okay, so then that means that you're not actually going to get the cross-section you need, you're always going to have a smaller cross-section. Let me write this in. So we need a cross-section like this, but you're going to get a cross-section that's smaller than that. If you have a cross-section that's smaller than that, then instead of following you down to the correct relic abundance, the annihilation is going to become inefficient too early, and you're going to freeze out to this higher plateau of dark matter. So what happens in these heavy dark matter models generally is that you overclose the universe. Like you get too much dark matter. So the ways to get around it are to dilute it somehow, which you can do if you heat up the standard model while not heating up the dark matter at the same time. So put more energy and entropy into the standard model bath. So that's one way to do it. So then you do that. The other way to do it, I mean, the paper that I worked on recently, another way to do it is if you have a first order phase transition, you can get enhanced local density during that first order phase transition, which basically turns the annihilation back on, and again, lets you do a step like this, so that you go from overclosing the universe down to the correct dark matter density. Does that make sense? So yeah, there are loopholes to the unitarity bound, but the loopholes all consist of having some way to do this. Basically, right? Having some way to deplete the dark matter abundance further after freeze out. The generic behavior is you get too much dark matter in that case.
Okay, thank you. It's clear now.
Okay, let's thank Tracy again. Now let's move on to the last lecture of the morning by Olga Mena on neutrino.
No? Yes, yes, and now yes. So experimentalists. How many of you are working with neutrinos, either in high energy neutrinos also? Any from Ice Cube, Antares? Someone? No? High energy neutrinos? Yes? Okay, very good. Gamma rays, how many of you? Okay. CMB? Galaxy formation, a large scale structure? Okay, very good. So I have more or less an idea of your background, okay. So I'll tell you about neutrino cosmology and astrophysics in these lectures, okay. I think that there is no need to further motivate the important role that neutrinos play in the universe, shaping the universe, right? In 2015, the Nobel Prize was awarded to Kajita and McDonald for the discovery of neutrino oscillations, which show that the neutrinos have masses, okay? And new discoveries about the deepest neutrino secrets are expected to change our understanding of the history, structure, and future fate of the universe. Here I put you some examples from the Forbes magazine, just emphasizing the important role that neutrinos have in cosmology and in our universe. So here is a picture of the photon windows of our galaxy in different wavelengths, right? So in the case of the neutrinos, we have something similar, right? We have neutrinos, this is the neutrino energy, which range from basically 10 to the minus 6 to 10 to the 18 eV, okay, in energy, okay? 10 to the minus 4, to 10 to the 18. We have the cosmic neutrino background, for instance, that is something that we are going to see in these lectures. And we have also ultra-high energy neutrinos and high energy neutrinos that we are going to also see in these lectures, okay? In the middle, there are many other kind of neutrinos, right? As, for instance, solar neutrinos, geoneutrinos, the diffuse supernova neutrino background, neutrinos produced in reactor, in atmospheric, or also cosmogenic neutrinos, that I will tell a bit about them. But, I mean, keep in mind that the neutrino window is as wide as the photon one, okay? Here again, the distance traveled by these neutrinos, the different neutrinos from this broad neutrino spectrum, versus the neutrino energy in EV, and all the windows that they open into physics, okay? So we can study dark matter, sterile neutrinos, neutrino cross sections, fundamental symmetries as CPT or Lorentz invariance, neutrinos which refer to cosmic backgrounds, flavor mixing, CP violation, mass ordering, Majorana versus Dirac. A lot of things we can study with this, from both the particle physics point of view and also the cosmology and astroparticle physics point of view, okay? So here I've shown you, right, this thing that is called the GCK cutoff. Let me explain you why is this. I mean, in 1966, these three scientists discovered why there should be a cutoff in the ultra-high energy cosmic ray spectrum. And it's due to the fact that cosmic ray protons with energies larger than this quantity here, than roughly 6 times 10 to the 19, interact with the cosmic microwave background to produce, via the delta resonance, these products, right? The threshold for these reactions can be computed as follows, right? The momentum of the photon plus the form momentum of the proton square should be larger than the mass of the proton plus the mass of the pion, right? And then you can apply in some kinematics, you can really get to this bound, okay? So keep in mind this calculation, because in the exercises you will have to do something similar. Of course, we will help you, no problem. If you have any, it's quite straightforward, but if you have any trouble, we will help you. Which means that the mean free path of the ultra-high energy cosmic ray, ultra-high energy cosmic ray that are reaching us today is just 10 megaparsecs, okay? A lot of activity is also going in the experimental field. That's why I ask if any of you are working in experimental physics. So, I mean, we have experiments that will cover basically all the neutrino spectrum. For instance, we will have short baseline and long baseline neutrino experiments such as Dune, Super K, with gadolinium, hyperkamiokande, Juno that will detect reactor neutrinos and also supernova neutrinos, neutrinos producing supernova type 2 explosions. We will have also in the high energy frontier Ice Cube, Antares, Came3Net, or also Earth shower experiments, right? Of course, we also have all the cosmological future experiments that are sensitive to neutrinos, okay? So let me start with the first topic, right? Which is the cosmic relic background, and let's study the cosmic the coupling of these cosmic neutrinos in the early universe. Okay, so this is a picture of our universe today. Okay, this is like a pizza where we have dark energy, dark matter, the cosmic microwave background with the relative abundances, right? I mean relative to the critical density today, and we have heavy elements, stars, hydrogen and helium, and also neutrinos. So the question is, how big is this neutrino piece, right? So neutrinos are kind of dark radiation, right? And you will tell me, but come on, I mean, radiation is visible. I mean, the CMB photon background, it has a black body spectrum with a mean temperature of 2.725 Kelvin. Of course, there are variations around this mean temperature. You have seen this already in lectures in this, and many of you are way more experts than myself on this, right? So this map, what is telling us there are fluctuations, is just how the CMB temperature varies with the different patches in the sky. Okay, so the CMB fluctuations, we have just seen this also in Tracy's lectures, right, are due to acoustic oscillations in the baryon photon fluid before recombination, that is, before protons and electrons combine to form neutral hydrogen, right? So the potential, well, in the early universe, photons and baryons are tightly coupled, right? They behave as a very, very tight coupled fluid, okay? So as pressure tries to compress these baryons and photons, right? As gravity tries to compress, the pressure will resist, okay? So it's an interplay between the radiation, okay, the pressure by radiation and gravity, okay? So the potential wells, which are associated to high density region, will be translated into cold spots because photons will lose energy to climb out from these gravitational potentials. On the other hand, the potential hills, which are associated to low density regions, will be translated into hot spots in CMB maps, okay? So here we see this beautiful picture from Planck and WMAP of these fluctuations, right? And you can see here how just by eye, one can really recognize, thanks to these maps, right, that the universe should be composed by both dark matter and dark energy. You can see these 5 differences even by eye between a universe with just atoms, I mean regular baryonic matter, let's say, right, or just a universe with dark matter and dark energy and 5% of baryonic matter, okay? So there are 410 photons per centimeter cube, or in American units, if you prefer, roughly approximately 7,000 photons per inch cube, right? So according to standard cosmology, there should be an equivalent neutrino background, okay? Albeit slightly colder, we are going to see this Y is colder, right? And there are 340 neutrinos per centimeter cube. If this cosmic neutrino that we believe is permeating the universe has never been detected directly, okay? Directly, there is no evidence for direct detection of this, okay? So the universe is filled with a dense flux of relic neutrinos created in the Big Bang. And this makes neutrinos the most abundant form of the hot dark matter, okay? Neutrinos are dark matter, but hot dark matter. So somehow we know that that dark matter is there because neutrinos are hot dark matter and should be there, okay? So let's start with the neutrino decoupling. This is the arrow in time, right? We are down here, okay? So neutrinos decouple, right, when the temperature of the universe was of the order of 1 MeV, and the universe was 1 second old, okay? So let's see what happens with neutrino decoupling. Let's see if I can, I went too fast. Okay, so we have just seen in Tracy's lectures, right, that a straightforward rule to compute the decoupling of a particle, right, in the early universe in the thermal bath is just that the thermally average interaction rate is when this rate gets equal to the Hubble expansion rate, right? This means that interactions cannot be kept in thermal equilibrium, okay? And the particle decouples. So, I mean, the neutrinos, as you know, all interact very weakly via weak interactions with the standard model of particles, and then their thermally average cross-section goes as GF, the Fermi constant square, times the temperature to the 5. And the expansion rate of the universe, right, goes as T square over M Planck, okay? The expansion rate. The square goes as T to the 4 times M Planck square. So this means that these two quantities are the same when roughly the temperature of the universe is 1 MeV, okay? So these neutrinos don't inherit any of the energy associated to electron-positron annihilation. And therefore, they are colder than photons, okay? So the neutrino temperature today is related to the photon temperature by this factor, which means that neutrinos have a mean temperature of 1.95 Kelvin, okay? That's approximately 10 to the minus 4 eV, okay? Why is that? So how are related this neutrino and photon temperature? Okay, where is it coming from, right? I mean, electron-positron annihilation takes place after neutrino decoupling, okay? In an expanding universe, the entropy density per moving volume is conserved, right? Is this quantity here. We have bosons, the entropy, the contribution to the entropy from bosons, and also the contribution to the entropy from fermions. Before electron annihilation, before electron-positron annihilation, we have 2 electrons, right? Two positrons, neutrinos, 3 antineutrinos, and photons with G equal to, right? The degeneracy. And therefore, this is the factor for the entropy, right? Before. After, only neutrinos and antineutrinos and photons, right? But at different temperature, because electrons and positrons have annihilated, okay? So neutrinos do not share in this entropy release. And therefore, the temperature, right? Their temperatures are related by this factor. So neutrinos are colder than photons today, okay? So we have just seen this, right? The neutrino decoupling in the early universe is quite simple. We will see that this is not as simple as this, but okay. So let's start now, let's continue now with N-effective. We have heard about N-effective many times today, right? And I guess that you have heard also last week. Okay, so what is N-effective? So the total radiation in the universe can be written as the photon contribution plus a dark radiation contribution, okay? Which is parameterized by N-effective. This is the number of effective relativistic degrees of freedom at the coupling, right? So in the standard scenario, it's not 3, it's 3.044 plus minus 2 times 10 to the minus 4. We will see now this, why, okay? And it's just electron, muon, and tau neutrinos. But neutrinos could decay over cosmological times, right? So there could be also less neutrinos, or there could be more neutrinos as indicated by, for instance, short wavelength neutrino experiment anomalies, okay? For instance, sterile neutrinos, which do not interact via the standard model interactions, so they in principle, I mean, they could be present also, right? So if they don't interact, right, you will tell me if they are sterile and then they don't interact, right, how do we measure them, right? Because, I mean, of course, this is the dark side of the gravitational force, okay? So sterile neutrinos will count as extra species, and then we can know about them just because of gravity, okay? So in this in simple calculation that N-effective is 3, there are many factors that one approximates, right? I mean, in the simple calculation, right? First of all, one is assuming that all particle species behave as ideal gases, okay? This is the ideal gas approximation. However, this is one of the most important corrections, but the most important one by far is the last here, okay? There are also approximations assuming that the neutrino decoupling process occurs instantaneously, okay? But the neutrino and the QED sectors, the quantum electrodynamic sectors, transit from a state of tight thermal coupling to just, but this is not true. It's not instantaneous. It does not happen like this, okay? And the electron-positron sector, another approximation is that the electron-positron sector is fully ultra-relativistic at the time of neutrino decoupling. That is that the temperature of decoupling over ME, over the mass of the electron, is infinite. This is ultra-relativistic approximation, but this is not true. Any of these assumptions is true. Of course, if you apply them, you will get 3, but I mean, sometimes, I mean, it's good just to have an idea, but if you want to compute things precisely, you really need to go really far deep into the problem, okay? So, I mean, let's start with the ultra-relativistic approximation, okay? Well, this is not well-satisfying reality, okay? And the breakdown of this approximation contributes the largest contribution to N-effective, okay? So, when we say 3.044, is coming basically from this approximation, okay? Because there will be a change in the QED plasma entropy density given by this expression, okay? When one does not apply this limit, okay? So physically, what does it mean, this correction physically? Is that electron-positron annihilation is not a temporarily localized thing, okay, at temperatures of 0.5 MeV, okay? So this is just to show you that when one does approximations, sometimes for calculations, one then has to account for corrections to this, okay? This is the most important one. Then we have another one, right? We have another one, which is that all particle species behave as ideal gases. Come on, ideal gases don't exist in nature. So, I mean, this is impossible, right? There are no ideal gases in nature. So in ideal gas, we have the electrons and the photons here, but of course, this is not true. You know, I mean, we know that there is a QED plasma. We have electromagnetic interactions, okay? So there will be a modified QED equation of state. And this is because particle physics is not as beautiful and as simple as when we see these beautiful pictures from the Atlas thing, right? No, I mean, there are many, many things behind, right? And what happens is that at finite temperatures and densities, right, the interacting quantum fields show features that they don't show at 0 temperatures, okay? And this, what will happen is that there will be corrections, right, to the finite temperature QED partition function, to the QED plasma equation of a state, okay? This is the partition function, and we will have corrections here, right, to this QED plasma equation of a state. And these corrections give factors of plus 0.01 or minus 0.05. And you will tell me, is this important? Of course. I mean, experiments at CMB stage 4 is aiming at precision of 0.04. This will mean that maybe future CMB experiments are able to test these deviations from the canonical 3. You know, I mean, this will be absolutely fantastic to test this, okay? So these corrections also apply to the effective for Fermion contact interaction, describing the neutrino-electron scattering processes, okay? So we will have modification of the dispersion relation, vertex corrections, emission or absorption, or closed fermion loops. These are not very important, are smaller than 10 to the minus 4, but still should be considered, okay, in the calculations. And then we have the last one, and this is the assumption of non-instantaneous neutrino decoupling, okay? And this will cause an spectral distortion of the CMB, of the cosmic neutrinos, okay? So neutrino decoupling and electron-positron annihilation are processes which are very close in time, okay? And it's not that one happens in inflation and the other one at the end of the universe, okay? So are really, really, really together, right? So none of these two events are localized in time. And there are really interactions still, right, between the electrons, positrons, and neutrinos at cosmological temperatures of the order of MeV and at lower temperatures also, right? So these processes, of course, are more efficient for higher energy with neutrinos with larger momentum, with larger energies, okay? And they lead to no thermal distortions in the neutrino spectra at the percent level, okay? So here you can see this effect, right? Well, the effect is not that large. The most important one is the ultra-relativistic approximation. But you can see this, that if you assume a relativistic Fermi-Dirac distribution, you will have this. And then the real thing is that the neutrinos at higher momentum are affected by this approximation, okay? So the last correction we have, right, is the one induced by flavor oscillations, okay? Here we can see that is 5 times 10 to the minus 4, okay? So you can see that this is an effective here, and these are the mass square differences as measured by neutrino oscillation experiments, and also the mixing angles. I will tell you more precisely about the mixing parameters later on, okay? But the effect is not that big. The largest effect is induced by the solar mixing angle, but it's not that large, okay? But also neutrinos mix with each other, right? Because the mass eigenstates are different from the weak eigenstates. So, I mean, we have neutrino mixing as we have quark mixing also, and although the structure of the matrices are quite different, so we have also corrections due to that, okay? Due to flavor oscillations in the early universe, okay? So if these neutrinos are massive, okay, their energy density is given by this expression, and their number density today is 56 per centimeter cube, okay, which is, if we sum the 3 flavors, electron, muon, and tau, plus neutrinos and neutrinos, we will get this 340, and this will be the exercise. This will be some exercise that you will have to do, okay? And then, okay, we have our first neutrino mass limit today. One can impose that these neutrinos don't overclose the universe, and then one gets, just by imposing that this to be smaller than omega c h squared, one gets a bound on an upper bound on the neutrino mass that is 0.45 eV. Okay, sorry, 45 eV, no, 0.45 eV. That is not very good, but okay, still is a limit, right? I mean, and it's a straightforward limit, right? So, I mean, this is quite easy, no? So, realize that these neutrinos decouple when they were extremely relativistic, okay? They had very, very large thermal, they were extremely relativistic, so they are hot dark matter. They have very, 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 very large velocity dispersions, okay? They are not like cold dark matter, okay? So the velocity, the thermal motion is really, really large. I mean, so the thermal motion for a 1 eV neutrino is comparable to the typical velocity of a dispersion galaxy. Here I show you the pinwheel galaxy, okay? It's a regular galaxy, right? With a typical velocity dispersion of 100 kilometers per second or so, okay? But there are much smaller objects in our universe, okay? As dwarf galaxies, for instance, right? As for instance, the small and large Magellanic Clouds, right? What happens with this is that neutrinos have too much thermal energies to be squeezed into small volumes to observe the smaller structures we observe today in our universe, okay? This is crucial. This means that neutrinos free stream, okay, wash out small scale fluctuations, not as cold dark matter, okay? So this means that neutrinos won't be able to cluster, okay, at small scales. And this is how we are going to learn about their mass, okay, precisely for this factor, okay, for this fact. So, according to neutrino oscillation physics, okay, we know that there are at least 2 Dirac or massive Majorana neutrinos. Why I say 2? Okay, massive. Because neutrino oscillation experiments have measured 2 mass square differences. One, here, the solar one, and another one, the atmospheric one. We don't know if the atmospheric one is positive or negative, which means that the solar doublet could be the lightest or the heaviest. This is in the normal hierarchy, this is in the inverted hierarchy, okay? So, neutrino oscillations can measure these 2 mass squares. But this implies that there could be only 2 massive neutrinos, because the lightest one, here 1 or here 3, could be 0. I mean, could have 0 mass, right? Okay. So also, from what I'm going to say today here and the rest of the days, there won't be any difference for Dirac and Majorana neutrinos, right? Except for one plot that I'm going to show you, that is the one that is measured by neutrinoless double beta decay experiments, okay? But from what I'm going to say, there won't be any difference, okay? So what do we know? We know for neutrino oscillations that at least 2 neutrinos have a mass above this value, right? Because at least 2 of them should have a mass above the square root of the solar mass difference, and that at least one of these neutrinos will have a mass larger than 0.05 eV. And this is very important for cosmological searches, okay? Why? Because this, right, what oscillation physics does is to put a lower bound on what we have to look from cosmology, okay? Here I show you the mass, the sum of the 3 neutrino masses, right, for the normal in red and inverted in blue, right, versus the mass of the lightest neutrino. You can see that this could be, I mean, even 0, right, so the mass of the lightest neutrino, versus the mass measured by tritium beta decay experiments, as the Catherine experiment, okay, and also by the mass measured by neutrinoless double beta decay experiments, which are those searching for the Majorana versus Dirac character, okay? I show you here also some sensitivities from future experiments. Catherine, the current bound from Catherine and the future Catherine sensitivity, and also from Cam-Lansen and future sensitivities. And more importantly, I show you here the current limits from cosmology of the neutrino masses. We are going to see this in detail. But today, basically, CMB tells us that the mass should be smaller than 0.24 eV, while if we combine it with measurements of the Sloan Digital Scale Survey 4, okay, we can get down to 0.9 eV. So, I mean, realize that cosmological limits are really testing the minimum mass predicted by neutrino oscillation experiments. This is really good, I mean, and really fantastic. It's like when NFT will reach this limit of plasma, of these corrections, of finite temperature corrections and such in the early universe, right? We are really testing, right, fundamental physics, okay? So, with cosmology. So let me go further, right? We have seen this already, and let me see how do we know about an effective from cosmology, okay? So let's go to BBN. I'm gonna go really fast in this BBN part because I think that today your head with BBN is already like, oh my God, again BBN. Okay, so I'm gonna go quite fast, okay? So you have heard a lot of BBN. You now are BBN experts, okay? So BBN, right, takes place during the first 3 minutes in the history of the universe. We are here, right? So Big Bang nucleosynthesis, and what it does is that it predicts the abundances of elements heavier than the lightest isotope of hydrogen, okay? Deuterium, helium-3, helium-4, and lithium, okay, which are settled, right, which are fixed by the first 3 minutes. And realize that we are observing these elements at late times, okay? So we have to go to places with very low metallicity, okay? I mean, with very little evolution. It's like if I show you a picture of a grandfather and I tell you, okay, full of wrinkles and so on, I tell you, tell me how was he when he was a baby. So you will tell me, okay, I mean, he's fully contaminated by all the background, right? I mean, so we have to go to places, we have to find pictures of this guy when he was 5 years old, or 4, or even 3 better, right? Because otherwise, no way. Okay, so this plot, Valerie already saw this plot. She explained it very, very well, much better than I can do. So, I mean, here I show you the helium mass fraction, right? So, the helium is good. Why? Because it's measured in low metallicity extragalactic H2 regions. However, it's produced in stars, bad. But still we use it for cosmological observations. Deuterium is good because it's measured in high redshift quasi-stellar objects, assertion lines, but it's bad because it's destroying stars. But we use it because I mean, measurements indeed of primordial deuterium are really, really good. Helium-3 is not good. It's not used because I mean it's measured only in the solar system and high metallicity regions, so no way. And then lithium, we have a problem with lithium. I mean the lithium is measured in metal poor stars in our galaxy, however it's destroying stars and producing galactic cosmic ray interactions. And moreover, we have this lithium problem that is unclear if it's really a problem in computing the primordial lithium abundance or a problem in measuring it, okay? This discrepancy. There have been ideas also beyond a standard model and things like that, but none of them is really convincing. I think that probably something in extracting this because it's measured always in places of high metallicity, okay? So for us, the important quantity will be helium-4, okay? Why? Because well, before going there, I'll show you here just briefly the uncertainties, okay, in this measurement. So you can see that lithium is very poor measured, but then is helium, then is deuterium. Sorry, then is helium-3. Sorry, deuterium and helium. Okay, the relative uncertainties. Okay, so deuterium and helium are really well measured. Okay, so. Briefly this, because we have seen it already in Valerie's lectures. So the nuclear binding energies are of a few MeV. That's why BBN occurs at these energies, okay? When the temperature of the universe is MeV, okay? So that we have several relativistic particles in equilibrium, photons, electrons, and positrons. We have the coupled particles already. When BBN takes place, neutrinos have already decoupled, right? And we have non-relativistic particles as baryons. But remember that are way less baryons than photons. We know this via the eta parameter, the baryon to photon ratio, okay? So neutrons and protons interact via these weak interactions, and light elements are formed via these interactions, okay? Deuterium, helium-3, helium-4, and such. So, I mean, for calculations, one assumes usually that heavier elements than helium and lithium are not formed, right? And then that at temperatures about 0.1 MeV, only free protons and neutrons exist. Okay, because at higher temperatures, each time a nucleus is formed, it is destroyed by high energy photons. Okay, so these are the calculations that one normally does, and indeed like this are quite simple. It's always the same formalisms, okay? So the most important thing that I want to keep you in mind, right, is that an effective, right, changes the freeze-out temperature of weak interactions, okay? Because if I add more neutrinos, right, I will have a larger expansion rate, right, in the universe, and a larger freeze-out temperature. So I will produce more helium-4, because the helium-4 is, the amount of helium-4 is proportional to the neutron-to-proton ratio. And the neutron-to-proton ratio goes like this with the freeze-out temperature. Here you can see clearly how, from this paper of Keith Olive and collaborators, that as I increase the number of effective degrees of freedom, the helium fraction really increases, right? So more radiation in the universe, more helium-4. That's how we are measuring an effective from Vivian, because of this effect in helium-4, okay? Very good. So let's move on and let's see how do we measure an effective at recombination, okay? So many of you are here, many of you are working on the CMB. So I mean the CMB, right, is also the CMB period is also known, right, as the photon decoupling, because photons started to freely travel through the universe without interacting with the matter, and the CMB gets frozen, okay? So I mean, this happens, right, when the universe was 300,000 years old. You know this, right? And here I show you the typical map, right? You have seen this in Fabio Finelli's lectures, I believe, right? And he explained this much better than I can do, but okay. So, I mean, we have several contributions, right, to this map, right? We have the different contributions from the different multiples. We are adding maps and maps and maps, okay? And as you know, I mean, so what we are doing when we observe these maps, right, is that we have a spherical harmonic decomposition, right? Because it is sort of a theorem. Any function that is defined on a sphere, as the photon temperature, can be decomposed in terms of spherical harmonics, okay? Keep this in mind, okay? So the expansion coefficients are given by this expression, right? And the angular power spectrum, the CMB power spectrum, measures the amplitude of the expansion coefficients, right? As a function of the wavelength. This is what it does, right? Here we see this example for L equal 4, okay? So you just to give you this picture in mind of what we are measuring, or when we are observing these maps, okay? So there is a lot to learn about in these fluctuations, right? In the CMB fluctuations. Here I show you the standard prediction from the lambda CDM model, together with measurements with Planck, okay? And here the relative deviation from the best fit model of these measurements, okay, in the lower panel versus the multiple, okay? So when we look into the very, very largest modes right here, we are sensitive to the initial conditions in the universe. Why? Because these modes are as large as the universe, right? So they were not inside the horizon at the time of the coupling. So they are not subject to this pressure radiation effect, okay, interplay, okay? So they are really sensitive to how was the universe in the very beginning, that is to inflationary processes. The second peak tells us about the geometry of the universe and also about the sum of the neutrinos, as we will see. The first peak, sorry. The first peak tells us about the geometry and the sum of the neutrinos. The second peak is a variometer. Why? Because the relative height of this will tell us about the amount of baryons in the universe, okay? The relative height of the second peak. And how do we learn about an effective? About the highest modes, okay? The highest multiple modes, okay? These smaller scales in the CMB are those which are telling us about an effective. I'll explain you now why, okay? Here I show you two maps, one with an effective equal 3 and one with an effective equal 6. Okay, you will tell me. So, bien, very good. I mean, let's call, because this is, okay, even myself, if I put these glasses, right, there is no way, right? But, of course, we can decompose this in terms of spherical harmonics, and you will tell me, okay, this is obvious, right? This is elementary, my dear Watson. Okay. You see an effective equal 6, 3, an effective equal 6 here, the deviations, and look at the error bars from Planck. I mean, it's obvious. I mean, you physicists, when you say that you are, it's because you are a particle physicist and not a pure cosmologist. I mean, no way. No way. Why no way? Because we are not measuring only this, okay? Okay, I mean, when we are looking into the CMB, we are measuring the baryon density, the matter density, the Hubble H, which gives us the Hubble constant, the amplitude of the primordial power spectrum, NS, tau, and effective. And this is if we are really modest, because we can extract also the running and the running of the running. And then, I mean, okay, so what it means is that if I play with these degeneracies, okay, I can really show you a curve here, right, with n effective, here we can see equal 6, that you can either see it, you see this red line also has an effective equal 3, okay, and is identical to the one with, this one in red has an effective equal 6, and is identical to the one in n effective equal 3, okay, and this is not elementary at all. So, I mean, I can play with the parameters and give you a model with an effective equal 6 that is the same than an effective equal 3. And why is this? This is because the only effect at small multiples that cannot be mimicked by others is this one, is induced by the anisotropic stress around the first peak. And this due to the fact that neutrinos are free streaming particles, right, that propagate at the speed of light and travel faster, right, than the sound speed in the baryon photon fluid, okay? Affecting the modes that enter in the horizon before the recombination. And this is the only effect that we can see in, for instance, in WMAP that couldn't reach very high multiples, okay? In Planck is different, but so to measure this, we have to go to very high multiples, okay? So if we go to the damping tail, as measured by the South Pole Telescope or the Atacama Cosmology Telescope, and now by Planck, right, we can see that higher and effective will increase the expansion rate and also the damping, okay? Because the diffusion length is inversely proportional to h, okay? So you can clearly see that as I increase the value of n effective here, okay, you can see that there is a damping of the multiples, okay? The only quantity that is degenerate with this is the helium, because helium affects this Ne. Ne is the free electron fraction times 1 minus Yp. So helium is a problem to measure an effective, right? But we know helium also from BBN, because we have seen that BBN also is sensitive to helium, right? Of course, I mean, we know that. So, I mean, this interplay is going to break the degeneracies, okay? But realize that to measure n effective from the CMB, we have to go to the largest multiples, okay? Otherwise, there won't be any effect, as I have shown you, just due to the fact that we have many parameter degeneracies, okay? So here I show you the measurements of n effective from the CMB, right? When NU is fixed, right? And when NU is not fixed. So you can see, right, that look at helium, how it changes. I mean, of course, here, helium is very well measured. If I have an effective as a free parameter, look how bad I measure an effective from the CMB, okay? Have you, lithium, helium from the CMB. So, helium without an effective being a free parameter, helium with an effective being a free parameter. Have you seen, right? Because there is a strong degeneracy with these parameters, okay? So, for model builders, bad news. N effective, perfectly consistent with 3, right? These are the plus minus 0.36 and 95% confidence level. If we are large-scale structure information, that we will see in the next lecture, or in the following one, let's see how far can I talk. So how fast can I talk? So this error is a bit smaller, but still the mean value is 2.99, okay? So no evidence for extra species. Okay, thank you. And this is perfectly consistent with BBN estimates, okay? You see here BBN estimates, the deuterium or helium, and then CMB. So no room for more species. Here I show you a slide I stole from a collaborator, Martina Gervino, and again, combining many different observations. Planck temperature plus polarization, Planck temperature polarization and lensing, in a universe with, lambda CDM plus an effective, perfectly consistent with 3. Even if we add n running of course, the same. Even if we are, well, in YP, you know, when we add helium, the error bars are much larger, of course, because there is this degeneracy from the damping tail, but still, the measurements are perfectly consistent with an effective equal 3, okay? So there are no hints for an effective equal larger than 3, at least in minimum extensions of the lambda CDM, okay? I mean, if you go to a model that is more complicated or has extra exotic interactions, but in minimal extensions, I mean, with a running or with a helium, or also with other things, is quite robust, this limit, okay? The prospects for the future are brilliant, right? Those of you working on CMB know this, right? So I mean, CMB stage 4 is gonna reach this precision, right? In an effective, here I show you the helium fraction versus an effective. This is these purple contours are those from a 95% confidence level from Planck, okay? So the first step will be Simon Observatory, which is gonna already reduce these uncertainties by quite a lot. And then we will have CMB stage 4. And as I told you, the idea is to reach in a precision in an effective, which can test this departure from these three. This departure that it was 0.044, right? That this would be absolutely fantastic. Because this would be an idea, a testing QED physics in the early universe, you know? I mean, another way of looking at this, right? So, I mean, another expectation, right? You can see the difference. These are these contours out are the BBN bounds, right? Okay, on the baryon to photon ratio and the neutrino number, right? And you can see the close contours are those currently obtained from CMB, right? And you can see here CMB stage 4 compare the size of this contour with the size of this, or the size of this contour with the size of this, okay? So this is just to give you an idea. This is the most complete one. This is only helium. This is only deuterium. If we combine helium and deuterium, right, we obtain this, and if we combine also CMB, we will obtain that, okay? And in the future, of course, the largest contour don't change because they don't have CMB, but the solid contours inside, right, they change a lot. I mean, CMB stage 4 will be a major step forward measuring an effective, okay? So we really are going to improve this. And of course, this huge degeneracy between the helium abundance and an effective will be decreased by these measurements. Also, a very important thing for those working on D-lens spectrum, the error in both in an effective and in YP, the 1 sigma error, is going to be reduced considerably if one assumes a D-lens spectrum. Okay, so you can see this comparing the blue lines with the green ones. Okay, so you can see that you can go from an error of 0.08 to 0.06, 0.05, okay? If we have with the lens spectrum, okay? So here there is something optional, but from those of you which are interested in knowing more about an effective and BBN, this is a very, very, it's a very useful code and it's straightforward. I say it's straightforward because I'm able to download it and run it. So, if I'm able to do that, it's because it's straightforward. Otherwise, forget about it, okay? So, you take this code, okay, if you want, and then what this code does is that you give an input value of an effective, and it will compute, right, all the BBN quantities. It will compute helium, deuterium, and then you can compare, right, this with observations. With CMB, with BBN primordial measurements, okay? So you just put your input values, okay, of an effective. For instance, you have a crazy model in which you don't have 3 neutrinos, you have 3.2 or 2.8, I don't know. And then you can use this code to infer what are going to be the primordial element abundances of deuterium, helium, and lithium, okay? So since I was going to stop here, but since the last part, which is high energy neutrinos, is quite heavy, heavy in the sense that it's large, that it has a lot of slides, I will start with the next thing, that is neutrino masses, okay? And then I will stop, and then you will ask me questions. Or if you want, I can stop now, and you can ask me questions, but okay, so as you prefer. So, yeah, okay. So, the sum of the neutrinos, right? So, let's go again to the CMB, okay? Again, the same I told you before. And now, let's see how do we know about the neutrino mass from CMB, okay? We have seen that N effective is measured via BBN, helium abundance, and also in the CMB via the high energy the high multiples, okay? Okay, the damping tail. Now let's go to the neutrino mass. And then the neutrino mass in the CMB, there are two typical effects. One is the integrated early Sachs-Wall effect, okay? And another one is a shift in the angular power spectrum. And here I show you the effect for neutrino masses of 2 eV, 1 eV, and 0.5 eV. You can see that there is a decrease in the first peak high, as I told you before, induced by the neutrino mass, and also a shift towards a smaller multiples, that is larger angular scales, when I increase the neutrino mass. And you can see this clearly, right? The deviation. As I increase the neutrino mass, the first peak high decreases, and the peaks are shifted towards that side, towards larger angular scales, okay? So why is that? Okay, so the early integrated Sachs-Wall effect. Here I show you the contributions to the photon temperature anisotropies. We have, the initial perturbation, if you want, right? The Doppler effect, and we have also here, right? This called Sachs-Wall effect. Why is this? Why is due? To what is it due? This effect, right? So in matter domination, the gravitational potential is constant. There is no ISW effect. However, the transition from the relativistic to the non-relativistic regime will get imprinted in this ISW effect, which is measuring, right, the time dependence of the gravitational potentials along the line of sight. Okay, so. And this will be imprinted near the recombination period, contributing to the ISW effect. Okay, so here I show you the relative contributions to the total photon temperature of these different terms. We have the Sachs-Wolf term here, the Doppler term, the total one here, and the integrated Sachs-Wall effect, which is small, but still is maximal around the first peak. Okay, so realize that a 1 eV neutrino mass will have a 10% effect in the CMB, in the CMB multiple, in the first high, okay? In the CMB anisotropies, okay? In the height of the first peak, okay? On multiples at these scales, okay? Basically, but there will be like a 10% effect for 1 eV neutrino mass. It's not much, because realize that we have plenty of degeneracies, okay? So you can also play with the height of these peaks, changing any other quantity, for instance, the dark matter density, right? For instance, or H0. So it's not a big effect, but at least is the one leading the constraints on the neutrino mass from the CMB, okay? This ISW effect, okay? And here you can see the decrease in the peak, okay? Also, there will be a shift in the angular location of the peaks, as I told you, right? Why? Because the angular location of the peaks, I think that you have seen this already in lectures, right, is given by the ratio of the sound horizon to the angular diameter distance at recombination. So, at the coupling. The sound horizon is given by this expression, is the maximum distance a sound wave can travel since the beginning of the early universe until photon decoupling, okay? And then we have the angular diameter distance, which is the inverse of the Hubble, parameter, okay? What happens is that the higher the neutrino mass, the lower the angular diameter distance. So peaks will shift toward lower multiples, right? But this effect can be compensated with a lower Hubble constant value. So there is a huge degeneracy, right? Sorry, there is a huge degeneracy here between the sum of the neutrinos and the Hubble constant, okay? You can see here that this is a plot from the Planck collaboration, right? You can see that, I mean, I can always compensate a largest value of the neutrino mass by changing by a lower value, I can always increase the neutrino mass, lowering the Hubble constant, okay? So what does it mean? It means that these, the degeneracies, right, are cancelled, right? I mean, that these two effects, right, are cancelled, basically. I mean, it's not that we cannot measure them, but there are so many degeneracies that these two typical effects in the Sachs-Wolf integrated Sachs-Wolf effect, and in the angular power and this shift are basically cancelled out by the degeneracies. So, and I finish now. So how do we know then from neutrino masses from the CMB? Okay, so it's due to gravitational lensing, basically. I mean, CMB is measuring the neutrino mass, basically, I mean, primarily due to the gravitational lensing of CMB photons, okay? So I show you here, just to finish with something funny, a movie, right, in which a spiral galaxy acts as a lens of a background quasar, and then this is the image we are going to see. You know that when the alignment between the source, the lens and us is perfect, we have these beautiful Einstein rings, right? So we have seen many of these Einstein rings, right? And here, for instance, we have something really nice, a double Einstein ring, right? I mean, this you can see an inner Einstein ring here and here another Einstein ring of 3 perfect aligned galaxies. There are less than 100 cases in the universe, and we have seen one. So in the next lecture tomorrow, I will show you how CMB can tell us about the neutrino masses due to lensing, okay? And I think I stop here because you are tired and hungry, so you are welcome.
Questions, comments for Olga?
I wonder, do you have the mic nearby?
They are tired. Oh.
No tired. We are young people. I'm sure they can resist a few questions more.
Yeah, that's true.
Thank you for your talk. You showed a slide that shows a correlation between the sum of neutrino masses and Hubble parameter, and
Yeah.
as I saw, it ends somewhere at 69. Does this mean that the value extracted from standard candles 74 contradicts with total neutrino mass? Like you have the lower bound from hierarchies. Does the value 74 contradicts to neutrino masses?
Yeah, I mean, what happens is that what happens normally with neutrino masses is that when you add bounds from as you said, the 74, you get a very tight bound, okay? You get a bound that is something like 0.07. You can even go down to 0.07, imagine. I mean, very close to the minimum value, okay? So this, I mean, should be done very carefully, okay? Because when you add this bound on the neutrino mass, right, the one coming from I mean, I don't know, I mean, whatever, Cepheids, right, observation measurements of I mean, local measurements of H0, you are really improving the bound. But I mean, you are combining two measurements that are in tension somehow, right? I mean, because if I add here a measurement of this, there will be here, of course, something like this, right? In the Hubble constant. Imagine here a contour like this, and then the neutrino mass will be, as I told you, I mean, 0.0 nothing. I mean, 0.006 or 0.0, no, not 06 maybe, but 0.08, you know? But, I mean, since these two measurements are in tension, right, I mean, I wouldn't say you can really combine them, right? I mean, of course you can do it, but was that your question or not really?
Yeah, like mostly it was, can we have the value 74 without contradicting the minimal limit for neutrino?
Yes. You are not gonna go down 0.06, this for sure. No. The limit will be something like 0.08 or something like this. But I mean, no, you won't really, but that would be really interesting indeed, by the way. That would be great. Imagine that tomorrow they come out with a super I mean, Gaia, whatever. I mean, they come with a measurement of the Hubble. Imagine, I mean, like 75 plus minus with a precision, and then you go down 0.06. Then, I mean, this will be telling us something about our picture of the universe. Maybe neutrinos, maybe neutrinos have extra interactions. Maybe there is something missing in the universe. This would be the most ideal situation, I mean, for us, right? Rather than, we are a bit stuck now with these two discrepancies, but yeah, it's still compatible, yes. 74 is still compatible, yes. Yeah.
Thank you.
Given the errors bars. Yeah.
More questions for Olga?
Hi, thank you for the nice talk.
Thank you.
I was asking that when this effective number of neutrinos are obtained, so these are done in Dirac picture, right? I mean, neutrinos are considered to be Dirac particles.
Yes.
Okay, so...
But Majorana won't change that picture.
Okay.
Do you know why? Because Majorana and Dirac characters can only be distinguished from each other in the non-relativistic limit. And we are measuring an effective that is the relativistic degrees of freedom, okay? At periods in which the neutrinos were extremely relativistic. You have to go to processes in which they are not relativistic, okay? And an ideal, something that was proposed, I mean, that you are doing high energy neutrinos, was that absorption of, the resonant production of C boson neutrino and neutrino of ultra high energy neutrinos with a relic neutrino background. In this case, the relic neutrino background, we expect that some of them are non-relativistic. And the target for a Dirac neutrino is half than that of a Majorana because they are in a non-relativistic thing. So you could observe, if you would have these ultra high energy neutrino beams and they would interact with the cosmic neutrino background, you will observe dips in the flux that are much deeper in one case than in the other. But remember this always. I mean, Dirac versus Majorana, you can only be sensitive to in processes in which they are non-relative. I mean, there is something non-relativistic because there is a mass insertion. Okay, in the process.
Okay, I had another question.
Mm-hmm.
Can any new physics scenario, can it affect the effective number of?
Yes, of course, many of them, a lot, many of them. Yeah. You mean relax the bound, or improve? Yeah, I mean for instance, any model including short baseline neutrino anomalies, right? I mean, as those observing reactors, right? I mean, that they point to an stellar neutrino, they will improve the number of neutrinos. I mean, so. The problem with this is that when you go to cosmology, but still there are solutions in cosmology. For instance, you can add an extra interaction that blocks. I mean, of course, this neutrino decoupling picture that I have just explained you is in the case that neutrinos don't have any other interaction than weak interactions. If you have there another interaction with an extra particle, with an exotic particle, it will block the thermalization of these neutrinos. So they won't thermalize. So instead of having 4, if you have an extrastellar neutrino, you will have 3.1 or 3. Playing with that. So yeah, you can avoid the limits, and there are many models in which you can avoid these bounds. Yeah, and there are many models that can produce extra radiation in the universe.
Okay. Thank you so much.
You're welcome.
Any more comments, question? Actually, I have one very nice.
Yeah.
Olga, is there any hope to measure the cosmic neutrino background?
Yeah, of course. There is this Ptolemy experiment that I will tell about it a bit more. That is is somehow similar to the tritium thing, but it's kind of you have to observe a kink it's a capture, right? So it's kind of challenging, this Ptolemy.
Because you mentioned this ultra high energy neutrinos.
Also, yeah. But you need a very, very high neutrino beam because you need to produce a C boson. You need a very, very high. This when you add these topological defects, decays into neutrinos, yes, but you need really. But the other thing is Ptolemy. I think that there was a poster of someone here of detecting. Yours, right? You was related to Ptolemy? Yes. Okay. So he's the expert. You should ask him. Oof. No. I think that is a great idea. Yeah. This would be amazing. I mean, amazing. I mean, this would be, indeed, imagine, I mean, there are 56, if we could do per centimeter cubic, we could do like this. So, I mean, Ptolemy is really, I mean, it's challenging, but I mean, I remember, I finished right now, the other day, I remember that I was reading the Scott Dodelson's book, that is like my Bible, okay, that I bring it everywhere, and it was written in the first edition that detecting the baryon acoustic oscillations would be a major thing. We have measured them today with 8 sigma precision. So, I mean, you know, I mean, Ptolemy should be a reality. I mean, you see, so.
We won't let you skip so easily. I have my own question. You flashed the very last few slides on lensing real quick. So I wanted to ask you the physical reason why gravitational lensing on the CMB was providing these constraints on the mass of neutrinos. It was neutrino masses at the end of your talk, right? So is it that you change the distances? Is it that you change the depth of the potential well?
Yeah, I mean, I will explain it better tomorrow, but I mean, what happens really, I mean, let's see. I mean, okay, you have this. You have the lensing potential, right? That is sensitive to both the matter distribution and the geometry. I mean, what happens is, I'll show you this, either this one or better the one of the Planck collaboration, okay, here. What happens is that neutrinos, right, they change this power spectrum, right? Because, sorry, I didn't show any plot, very good. So, now, here, right? So, I mean, they change this power spectrum, right? They reduce the power spectrum. So, I mean, they reduce CMB lensing. You see, as you increase the neutrino mass, what happens is that you are reducing the amplitude of the fluctuations.
You reduce because of free streaming.
Exactly, that's it, because it's always, I mean, the effect is based on that. Is that because they free stream, they don't contribute to small scales, and then what they do is that they just decrease lensing, right? So,
however, in the previous plot, you said that neutrinos would shift the peaks.
Yeah, but this is degenerate with H0, basically.
Right. Okay,
or with many others.
But you're essentially changing the angular diameter distance.
Yeah.
So does this angular diameter distance also reflect in this equation that you have here on the top?
Well, I mean, here you will have that, but I mean, you will have also this effect here. So, I mean, somehow you can really break the effect. You know, I mean, you are sensitive via this and via this. Okay. You know, so I mean, yeah, exactly, okay. And also via HFC, of course. But you have the most important thing is, as long as you are sensitive to the matter distribution, you are sensitive to the neutrino mass. And this is really, really how they measure it. Because I mean, when you add lensing, really you get these bounds. Yeah, I mean, yeah. So, but we will see this better tomorrow. Also, when we add large scale structure and such. Okay. It's also because I run a lot because I want to tell them about this ultra high energy stuff. That now we have this evidence from there was this beautiful thing from this hidden black hole from ice cube, right? I mean, so. Anyways.
Nice. No, thank you. Thanks a lot.
No, you're welcome. Okay.
Oh, there's one last question here.
Yeah.
Yeah, I just wanted to add one last comment, which is, yeah, these n-effective bounds and these upcoming n-effective bounds are really amazing. And just to tie it back to what I was talking about, one thing, in terms of the new physics that they can probe, these are a really powerful probe of dark matter models where the dark matter is totally secluded from the dark matter, doesn't necessarily have any interactions with the dark matter, or if they did, we're in the early universe, but you can still potentially learn about them from the presence of light new degrees of freedom at BBN and the CMB epoch. Yeah. And with these upcoming bounds, it'll actually, the bounds may get so good that you can test the scenario where dark matter was once in thermal equilibrium with the standard model before the electroweak phase transition. Yeah. And then since then, the standard model has been heated up by all the standard model particles decaying away, and the dark matter hasn't, so it's much colder, like the neutrinos, but supercharged, because the upcoming n-effective bounds will be good enough to see even like single new degrees of freedom in a secluded sector that decoupled before the electroweak phase transition, which is just amazing. It's just an incredible measurement. So yeah, and of course they're
this is to motivate. This is to further motivate people working on CMB. You know, I mean that you are doing really something important. The rest of course as well. I mean, thank you, Tracy.
Okay, let's thank Olga and Tracy. And remember, we will have a picture of the school now. I think there will be a photographer waiting for us outside. I think we're going to go on the roof of the museum, but I'm not completely sure. Thanks.